Welcome to the lectures of the course in Probability and Information Theory. So first let me give you a little bit of description of how the course will work under these very particular circumstances. So these video lectures are going to be just an introduction to the lectures that I will post on a website that I will send to you, and so your task would be to watch these video lectures, then to look at the lecture notes where you will find a lot more detailed description, and at the end of each lecture there are exercises that you are strongly suggested to do. And after the, so each week will consist in 3 lectures, and I would like to have a in-person meeting with you to discuss the content of these 3 lectures at the end of each week. So we can also organize other sessions if there are burning questions, but this is the initial setting that we will follow. Okay, so I'm Matteo Marsili. I'm a staff scientist here at ICTP in the Quantitative Life Science section, and my email is marsili@ictp.it for any question you can have. So let me start by giving you an overview of what this course will deal with. So first of all, the course is divided into 2 parts. The first part is a part that will take almost 1 month, or say 12 lectures, and it is based on how we go on translating a real world problem, a question that we have on a real world problem, into a mathematical model and into a calculation that then we can compare with data that we can measure in the real world by experiments. And so what I will focus on is mostly computing probabilities, and for doing this what we will be mainly concerned with is classical probability. So most of the calculation will be about solving counting problems. So this is why I like to call the first part of this course learning to count. So the second part of the course instead addresses more advanced subjects, such as the relation between probability and information theory, and also what we will discuss in the second part of the course is the behavior of large random systems. So systems that are composed of many random variables, and what one finds is that in spite of these systems being random, when the size of this system gets very, very large, their behavior is not random at all. So these systems display what is called a typical behavior. So to give you a sense of an example of this typical behavior, you can think at the central limit theorem. For those who already know what this is, this tells us that when we sum many random variables, and so the sum, which is the sum, has a behavior which is universal. Okay, or another result that we will discuss in depth is the law of large numbers, that tells us that if we take the average of many random variables, then this converges to a number which is not random at all. Okay, so this is what happens most likely. So this is what happens typically. Okay, and the understanding of this typical behavior will be a central part of the second part of the course. So what we will also study is atypical behavior. So what happens when we have large deviations from the typical behavior, and how do these large deviations typically occur, or how do they manifest? Okay, so this is a subject which is called large deviation theory, usually thought to be advanced, but as you will see, the understanding of these two aspects is very much related to a broad range of disciplines, and that go from statistical mechanics which essentially deals with describing the behavior of macroscopic systems, to problems in statistics and inference, that to some extent is the inverse problem of statistical mechanics, because in statistics and inference you want to understand what is the model that is generating a certain, that underlies a certain behavior that you observe in the data. And also topics in computer science that are related to information theory, such as coding theory or the theory of complexity. So essentially the aim of the second part will be to give you a language, a common language, a unifying language, a set of concepts that allows you to describe or to understand problems in these three different domains from a probabilistic point of view. Okay, so let's start, however, with the first part of the course. So what I told you we are going to do is to look at how we go from a problem in the real world to a description of this problem, which is a description in words, to a mathematical model, and finally to a calculation. Okay, so this is essentially how science proceeds. I mean, you are interested in a phenomenon that occurs in the real world. You try to formalize it first informally, then formally. Then you perform a calculation, and then you compare this calculation, what you get from this calculation, eventually with experiments that you can do in the real world. Okay, and if this calculation agrees with the outcome of experiments, then you can say that you have captured some some relevant aspect of this phenomenon. Okay, so so let's focus on these 4 aspects. First of all, phenomena that occur in the real world. So, of course, we would like to be able to solve problems, relevant problems, such as finding a cure for Parkinson's disease. But actually, what we do in science is that we study very different problems, okay? Much simpler problems, okay? So let's start from one of the first prototype questions that was asked in science. This is essentially how objects fall when they are fall from a certain height. Okay, and this is the typical experiment run by Galilei, and he went on top of Pisa's tower. I mean, this is a simplified description of what he did, and he let objects fall from a certain height, age, and he measured the time that it took for this object to fall, and what he found is that for different values of age, he found that the time was essentially following a relation, a quite precise relation, which is essentially given by what we know now, integration of the law of motion, of say Newton's law of motion. Okay. Now this is so of course it is remarkable that these 2 quantities depend with this particular shape, but what is most remarkable is that this phenomenon, this law, does not depend on many things. It does not depend on what is the color of the object. It does not depend on what is the time of the week. It is essentially the key point in this phenomenon is that it is a phenomenon where the behavior of the real world is actually very simple. It depends on very few variables. Okay, of course, this is not true for all phenomena. For example, if we want to understand Parkinson's disease, it is not by no means clear that this is something that will depend on few variables. That will be just some, say, key genes that control everything, and that we have just to find them. So part of science is choosing experiments or phenomena that have this type of simplicity. Okay, so and if you think about it, so these are also phenomena which are very unnatural, because so of course you can think of what contemporaries of Galileo was thinking about him doing this experiment. And but also, if you look at more advanced experiments, such as those that occur in CERN, so there you see that nature is really put into very extreme and unnatural and uncommon conditions, and under these conditions we get very predictable behavior. Okay. So the other thing I want to mention is that, of course, when you do an experiment like this, there are experimental errors. And these experimental errors depend on the fact that when you do this experiment, you should be it is not really true that this time only depends on the height. It also depends on the humidity, there is friction, there are a lot of other, wind is also affecting this phenomenon. So, and these other aspects are responsible for this deviation that we see of these experimental results from this theoretical behavior. Now, of course, what one can do is to do these experiments in much more controlled situations so that one can reduce these experimental errors to a large extent. But there will always be part of this phenomena, part of the aspects of this phenomena that one is not able to control, or one is not able to know. And so we call these experimental errors, but of course there is no mistakes in how things fall on the ground. It is rather than errors, it is more what we neglect or what we are not able to control that is causing these deviations. Okay? And the other thing is that what you find is that even in this case, the behavior that you observe is the typical behavior, is the most likely behavior. So even this statement here is a probabilistic statement in the sense that if you do this experiment, it is very likely that you will find that the time is close to this theoretical prediction. It is very close to this theoretical prediction. Okay? Okay, so let me go to the second aspect about a description of a problem we might be interested in. And let me start this description by an example. Okay? So let's imagine that we want to compute the probability of a single a single pair at poker. So we want to compute this probability, and so the statement of the problem is very simple. Is this one? So, but besides what is written in the statement of the problem, there is a lot of information that is not written there. Okay. So, for example, of course, there are a lot of. So, if you think about the real world phenomenon that this question refers to, well, it's a question where there are eventually some players playing poker, each one is dressed differently, etc., etc. So there are a lot of irrelevant details which are not in the statement of the problem, and this is because they are not relevant. So this probability is going to be the same no matter how the players are dressed, or no matter what is the time of the week, or etc., etc. Okay, so then there is a lot of common knowledge. So common knowledge means that it is assumed in this statement that we know what poker is, how it is played, and it is played with a stack of cards which has 52 cards of 4 different types, numbered from 1 to 13, etc., etc., and that a single pair is a group of 5 cards two of which have the same number, and this number is different from the other three, and single means that these other three do not have all different numbers. Okay? So this common knowledge is necessary to answer this question, because it is necessary to do the calculations. Then there is a lot of implicit information. There is also relevant. So I mean, what is relevant here is to understand how these 5 cards are selected. And there is nothing in the statement of the problem that tells us how these 5 cards are selected out of the 52. Okay, so if this is not stated, then it means that any 5 cards has the same chances of being selected as any other group of 5 cards. Okay, so by this, because otherwise, if a particular group of 5 cards were more likely to be selected than some other group of 5 cards, then it should be stated in the statement. Okay, and there is only one way which is consistent with the fact that it is not stated, that this probability should be the same no matter how the 5 cards are chosen. Okay, so this means that every group of 5 cards has the same probability, so that essentially we just have to count the number of ways in which in a group of 5 cards we find a pair out of all possible groups of 5 cards. So this means that in the end, in this case, going to a calculation, what we have to do is to count. Okay, so let me go to the next question. Actually, if you do this calculation, then you will find that this probability is essentially 42%, more or less. Okay, so let me go to the third aspect that we will see in this first part of the course, which is about mathematical models. So, in order to discuss this issue, let me take another example. So let us compute the probability that in a group of people there is no one that has a birthday on the same day. As someone else. Okay? So we want to compute this probability. So imagine that there are n, so there are, say, r people. Okay, and we want to understand what is the probability that none of these r people is born on the same day as someone else. Okay. So again, there are a lot of things that is common knowledge. What is a birthday, etc., etc., and there is a lot of implicit information. But now, so if you look at implicit information, that if we do not know anything, then what we can assume that for every person, every day is equally likely as a birthday, as any other day. Okay? This is strictly not true. This is an approximation because if you look at real tables in statistics, you will find that there are some periods of the year that are more likely than other people of the year as birthdays. But we will make this approximation that that every day is equally likely as any other day for a person to be born. And then under this approximation, what we see that this problem becomes equal to the problem of distributing R balls into n boxes, and to ask the question, what is the probability that there are no, at most, one ball in each box? Okay, so this is a classical problem in probability theory, which is the problem of distribution of balls in boxes. And so there are many problems that there are many questions like this one that can be mapped into problems such as this one, of distribution of balls in boxes, or of drawing balls from an urn, or of other prototypical problems in probability theory. Okay, and so it is important to study these prototypical problems in probability theory, because they allow us to answer many of these questions. Okay, so in particular, if you want to answer this question, again, this is a problem of counting, and so what you can do is to count in how many ways you can put these balls into the boxes, and you can think, well, I can put the first ball into n boxes, the second ball into n boxes, etc., etc., up to the last. For the last, I can choose n balls. So this is the number of possible cases. And the number of cases such that this event occurs is computed by taking the first ball, and this can go in any of the n boxes. The second ball can go in n-1 of these boxes, because it cannot go in the box where the first ball is. And the third in n-2 boxes up to the last two. Okay, so this is this in the end is going to give you the answer that is n to the r times n times n-1 up to 2 and 1. Okay. And okay, so as you see from these two examples, in many cases solving problem in probability amounts to counting, and this is what we will describe in. We will spend quite some time in this course on solving counting problems. Okay, and the other thing. So one particular tool that we will introduce for solving counting problems is to use functions, and to use what I call generating functions to solve these counting problems. And And the other thing which will be important is that when we do this calculation, it's also important to understand what are the variances and what are the symmetries which are in our model, because there are probability distributions which incorporate these invariances and symmetries, and so this allow us to do the right. This will allow us to do the right calculation. Okay, so this is a little bit the outline of what we will do in the first part. So